to x. Now, you might be asking yourself, why is that all we need to check? And that's a little bit beyond what I want to get into, all right? We could get into why that condition has to be met, but then you can start getting into some deep water, all right? So we will just take it on faith. Is that okay? All right. So that's a simple check, isn't it? You just can check some partial derivatives, see if they're equal. If they are, you're conservative. And if you're conservative, then you're path independent over any closed curve. So is this vector field conservative? This shouldn't take us but a few seconds. So I'm going to call this one right here P. Call this one right here Q. And I'm just going to do a quick check. Is the partial of Q with I keep on doing it backwards. I did this in the homework also. I'm going to follow the notes. Here's what I'm checking. Is the partial of P with respect to Y equal to the partial of Q with respect to X? Yes or no? Well, what's the partial of P with respect to Y? 2x. What is the partial of Q with respect to X? 2x. These are the same? Check. It is conservative. But that means, right, that means that f is equal to the gradient of some scalar function. Guaranteed. What don't we know, though? What is that scalar function, right? What is the scalar function? Do you think it's useful to have what the scalar function is? Do we even need it? On a closed curve, you wouldn't. But on just a regular curve, if you wanted to do the line integral, you would need to know the value of little f at the two endpoints. So I actually need to know what little f is, don't I? In order for me to do this? Right? Integral. That's the fundamental theorem of line integrals, right? That's it right there. So if this is if capital F here, vector, is the gradient of f, which it is in this case, then I would just need the two endpoints of the curve, which would probably be easy for me to get, but I would also need to know the scalar function. So this test just allows us to say yes or no, it's conservative, but the next natural question is, how do we find little f, right?
So if it's not conservative, then I'll go.
If it's not conservative, then there's no need to go look for it. All right. So if you know that capital F is conservative, right? If you know it's conservative, then we want to find the little f that creates that vector field, right? And that little f is called the potential function. That's what we call it. And now we actually go through the process of how you find potential functions. And we use what's called partial integration. Not partial differentiation, but partial integration. So let's do it. So first question, is this a conservative vector field? This is a different example, isn't it? So call this one right here, call that P, call this one right here Q, and do your quick check, right? I'm going to check my partial P with respect to Y, and I'm going to compare that to partial Q with respect to X. What is my partial of P with respect to Y? 2x, that's it? This isn't the same one, is it? No, okay. And then the other one, partial of Q with respect to X, 2x. It's not always 2x, okay? So it is a conservative vector field, right? So it has a potential function, and we need to be able to find it. So let's find it. So I'm going to write down what I know. I know that capital F is actually the gradient of little f, which I know by definition is this vector, right? Which for us in this particular problem is 1 plus 2x y plus natural log x comma x squared. Right? That's what I know right now. I'm going to start by writing down the first kind of solid piece of information that I have. And that is, I know that whatever f is, right, that its partial with respect to x is that. Right? That's what I know. So I'm going to write that down. Everyone understand what we're looking for is little f? Right? Okay. So I'm going to write this down. I have that the partial of f with respect to x is 1 plus 2xy plus the natural log of x. That comes from taking the derivative of little f, right, with respect to x. What I'd like to do is go back to little f. So I'm going to integrate this. Do you agree with this? Little f should be equal to the antiderivative of the little f, the partial with little f with respect to x. Do you agree with that? But that's just the integral of this thing, 1 plus 2xy plus natural log x with respect to x. Maybe I should have put dx in here, sorry. Do y'all follow what I'm doing? Going backwards, integrating. The reason we're calling it partial integration is because we're integrating with respect to only one of the variables. Right? We have two. So just think backwards now. What's the antiderivative of 1 with respect to x? Just be x. What's the antiderivative of 2xy with respect to x? X squared y, right? And just double check. If I take derivative of that with respect to x, I would get 2xy. What's the antiderivative of the natural log of x? Well, that's from Cal 2. I know in my Cal 2 class, we do it once and I give them the formula. I let them write it on their formula sheet. But if you tried to do that integration on your own like this, you could do integration by parts to get this. It turns out to be x ln x minus x. Okay? Is that all right? Take that on faith? Yeah. This is the antiderivative of the natural log of x. But anytime we integrate, we always had this what at the end? Plus a constant. And this is where things are going to get a little tricky. All right? Because I cannot just put plus c. And the reason is because what if this over here, I'm just going to show you just for demonstration. What if this over here said plus y cubed? Would I know the difference? Like if I asked you to take this right now and differentiate it with respect to x, would you get this? Yes. Yes, because when you got to y cubed, you would say the derivative is what? Would be 0 with respect to x, right? So you don't know if this back here is a constant or possibly something with y's. Understand? It could be a constant or a function of y. So what we do is instead of saying we have a constant of integration, we actually have a function of integration. And here's what I can tell you about that function. If it has anything in it that's worthwhile, it's going to have y in it. Right? It may turn out that this doesn't have a y in it, but it could. Right? Understand this? Sure? Okay. Now, I did see some x's canceled here. Did anyone see that? So where I am right now is I'm saying that little f is equal to x squared y plus x ln x plus some function of y that I don't really know what it is, if it even is anything, right? So we're getting closer to knowing what little f is, but we still have this gray area right here that we're not quite sure of. Yeah? Okay, so now I'm going to move to the next part. I'm going to use the other piece of information that I'm aware of. The other valuable piece of information that I have is that this this piece right here is actually the derivative of f with respect to y, isn't it? So I'd like for us now to take what we know about f, which is this, and I'd like for you to take the derivative of it with respect to y. So what is the derivative of f with respect to y based off of what we have here? So what is it? X squared. Derivative of this with respect to y? 0, right? That's all x's in there. Those are all constants. What's the derivative of g with respect to y? G prime of y, right? I'm going to write it this way. That's okay. That means the same thing, right? We're taking derivative with respect to y. Understand? But I know that that has to be equal to what? X squared, right? But this must equal x squared. So I'm hoping that you're seeing that this piece right here came from what we've developed about f, and this piece right here comes from what we know we have to have. So we set them equal to each other. And if you look at this just as an equation, right, you can subtract x squared on both sides, and you would get what? The partial derivative, or the derivative of g with respect to y, must be 0. Now, can you tell me what g of y is? Because that was the only piece that we didn't know, right? Here was little f. That must be a constant. Right? G of y must be a constant, because the derivative of a constant is 0. Now, be careful here. Could g have an x in it? No. Because we said when we were going back here that the worst case scenario is that this has y's in it, right? Or a constant, but no x's. Because if it had x's in it, then that would have contributed to our derivative earlier. So I know for sure that doesn't have x's. So when I integrate this, the only thing it could possibly be would be a constant. So that means that g of y, not derivative, that's derivative, this is g of y, is equal to some constant. You can use c, anything you want. I think the book uses k, but I'm going to use c. So c is a constant. And that's it. You're there. Tell me what little f is. Little f is x squared y plus x ln x plus c. Now, if you want to, you could write, instead of little f, you could write f of xy if you didn't want to write little f like that. And the good news is that when you find a potential function, you can always check your answer, right? You just take the gradient of it. So if I take the gradient of this, I should get this. Check it for yourself. It should work. Okay, any questions? Sure?
For g of y,
Uh-huh.
say it wasn't just x squared and it had something else with it.
Yeah.
It would be the same concept though. As long as it cancels
Let's see if
out.
we can do one where that doesn't work out so nice.
Okay.
Yeah. I'm hoping that I have another example where that doesn't work out so nice, but something's telling me that we don't. Okay, so look, here's a great problem where, again, you can go down the wrong road on this problem very quickly and start thinking, second guessing whether or not you really should have taken this class. And then you realize, wait a minute, hold on, there's got to be an easy way. All right, so we're being asked to compute f.dr, right? f.dr. Here's our vector field. That look familiar? That's the vector field we just had, right? And we're given this curve right here. Your two choices are to go ahead and find the derivative of this, which would be your dr. And then you could plug in for x, t squared plus 1, and for y, you could plug in t plus 2, right? And then you could dot the 2, and then you could integrate, right? You could do that? Do you all understand what I'm saying you could do? But that's way too much work. If I can somehow determine that that's conservative, right? If this is the gradient of little f, if that's what that is, then I know the answer to this is just little f evaluated at the two endpoints of the curve. In the previous example, we showed that this was conservative, right? And we found little f. And it turned out to be, you tell me I forgot, x squared y, x ln x plus c, right? That's what it was. So that's from the previous example. So all I need to do is take that function and evaluate it at the two endpoints of this curve. So I'm going to need to know what is R of B, which this is the same as saying what's R of what? Two, because this is RB, right? This is RA. And what is R of 2? So plug 2 into this. What do you get? The vector 5, 4, understand? Then I need to figure out what R of A is. That's R of 1, which is the vector 2, 3. Okay? And so to answer this, I just need to do f of the vector 5, 4 minus f of the vector 2, 3. And we said a second ago that all that really means, right, is plugging in 5 for x and 4 for y into the scalar function. And then plugging 2 for x and 3 for y into the scalar function. What's going to happen? Any questions before I erase this part? What's going to happen to the plus c? They will cancel, right? So I'm going to continue this. This is equal to, let's plug in 5 for x and 4 for y. So 5 squared, 25, right? Times 4 is 100. Plus x, which is 5, natural log 5. So 5 ln 5. Plus some constant. That's what I get when I plug this point in. Then minus, now let's plug in 2, 3. So what would you get if you plug in 2, 3? 12 plus 2 ln 2 plus c, right? And when you subtract all these, the c's will go away, won't they? 100 minus 12. 100 take away 12, 88. Plus 5 ln 5 minus 2 ln 2. You could leave it like that. You could also use properties and bring your 5 up, bring your 2 up, and then turn 2 logs into 1 log using subtraction. But, I mean, we're there. So look, before today, right? Before today, if I would have put this on the board last class, without the fundamental theorem of line integrals, you would have gone through and plugged each of these components in for x and y, then dotted that with the derivative, and then set up the integral from 1 to 2, and then ground the whole thing out. This new theorem allows us to do it a lot shorter as long as we can come up with a potential function. But it requires it's conservative, right? No conservative, not conservative, no go. And you're stuck with the old way. So I believe on your take-home test, I do give you a vector field that is not conservative, that you have to do the hard way, the long way, and one that is. And you have the choice on that one. Okay, what we have not seen, all right, is how we would determine if a three-dimensional vector field is conservative. And I said, stand by, we will do that. But if it is, we still have a way of getting its potential function. So I'm going to tell you right now, this is a conservative vector field. All right? I'm going to tell you that. And what I'd like for us to do is go ahead and find its potential function. Let's go ahead and do it. Does everyone understand that you don't have a way of determining if that's conservative yet? Right? Okay. It's three-dimensional. All right, so what we know is that this piece is the partial of little f with respect to x. This piece is the partial of little f with respect to y. And this piece is the partial of little f with respect to z. Assuming that it is conservative.